So in this video, we're going to talk about surface area, and it's going to build on what we saw previously when we were talking about arc length. So with arc length, we were measuring the length of some curve. For surface area, we're going to talk about the specific case of volumes that are found by doing rotations. So suppose I take this curve, maybe from this point A to this point B, and I rotate it around the x-axis. And already I got a little smeared, but it's going to be something that looks like this, right? Right, so this is my volume of rotation, that I've just taken this curve and I've spun it around the x-axis, and it's of some function f of x. And we want to approximate what's this outer surface area, right? That this portion along the outside. Really, we did volumes of revolution. Now we want to know the surface area along the outside, and we're going to use the same sort of method that we did previously. So last time we talked about how we took our curve and we split it up into little line segments L, that I can split this up into a bunch of pieces. And we're going to do the same thing here. In this piece, you can visualize this as a distance L, just as we did before. But in this case, this L is forming a band that wraps around the x-axis, right? That's sort of a band that looks like that. And we want to find what is the surface area of one of these bands. So let's take this band out and look at it sort of in isolation. Just like we found, and maybe I'll call it the ith band, because we're going to break this whole shape up into a bunch of different bands. And we want to look at the sum over all of them will give us the total surface area. So for one band, we're going to consider it having width L. And recall from our last video that our L sub I we found from Pythagorean was the same thing as the square root of delta x squared plus delta y squared. And using the magic of calculus that slope is just delta y divided by delta x, we were able to get the formula that L sub I is equal to 1 plus our derivative function evaluated at an ith point squared times delta x, right? So that's just what 1 L sub I is. But we want to know what the surface area of the entire band is. So for this entire band, this forms a circle, right? That this is a circular shaped, sort of slanty shaped circular piece. That a circle has circumference given by 2 pi r. And in this case, r is going to be the distance from the center of circle up to the height. So r is going to be from here up to the function f of x. So we can see from our image that this is going to be 2 pi. Our radius is the distance from the center of rotation up to the function, which is 2 pi times f of x. That means that the surface area of one band, or belt, this is sort of a belt, I'm calling it a band, anyway, is going to be equal to this length, L sub I, times the circumference around, like sort of height times circumference, which is 2 pi times f of x. And plugging in what we know about L sub I, that means that the surface area of one band is going to be given by the square root of 1 plus f prime of x sub I squared dx times 2 pi f of x. But we don't want one band, right? We want to have all of the bands, and so we're going to add up all of the bands, the sum of every single band from I equals 1 to n, because we're assuming that we've chopped this up into n pieces, of the surface area of each band. And then we want to take the limit as n approaches infinity, that we're going to break these bands up into skinnier and skinnier pieces, so our approximation is going to get closer and closer until it finally converges on the integral, which tells us that the surface area of this region of rotation, this is my abbreviation for surface area, is going to be given by this expression, right? Because this is surface area of one band, but we're going to integrate from A to B of the surface area of one band, and I'll simplify it a little bit in just a second. 1 plus the derivative squared, all square rooted, and before I was putting these in brackets to really emphasize the fact that you take the derivative first and then square it. And then instead of writing my dx here, I'm going to also multiply by 2 pi f of x, because this is the circumference of each of these circles, dx. So this is my equation for surface area. Usually we pull the 2 pi out front and rewrite this as 2 pi times the integral from a to b of f of x times the square root of 1 plus f prime of x squared dx. Right? So this is our formula for surface areas. But this only gives me the surface area of this outer part around the edges. It doesn't give me the surface area of this base of the volume or of this sort of back base back here, right? Because it has these two circular bases, and that's not being found in this surface area. It's only the red bands around the outside. So using this formula, let's go ahead and compute an example. And like we saw with arc length, it's frequently the case that you can't actually compute it by hand. So let's look at this example. Suppose we wanted to find the surface area of revolution of the function y equals x cubed on the interval from 0 to 1 about the x-axis. So recall that y equals x cubed is a function that sort of looks like this, but we're only interested about it. We are only interested in what happens on the interval from 0 to 1. And we want to take this and rotate it about the x-axis. So we're trying to find the surface area of this part that's of the rotation. We're ignoring sort of the base circle part, that this sort of looks like a cone on its side. And we're going to find the outside area. So to remember my formula for this, I always sort of draw in one of these representative bands, that I know that for any individual band, it's going to be the circumference around, which is 2 pi r, times the length of sort of the height of each little band width, which is given by L. So that means that the surface area is going to be given by 2 pi times the integral from 0 to 1 of 2 pi r is the circumference, and r is the height of this function in this case, which is given by x cubed. And then I'm going to multiply it by L. L in this case is the square root of 1 plus the derivative squared. And it's important that we take the derivative first and then square it. This is an easy enough derivative that I'm going to do it in my head. I can say the derivative of x cubed is 3x squared dx. So I've set up my formula to find the surface area of this volume of revolution. This becomes 2 pi times the integral from 0 to 1 of x cubed. I'm going to simplify the interior of the radical really quick. This 3 is squared, that makes it a 9, and the x squared is also squared, makes it an x to the 4th dx. And in this particular case, I look at this and I see that I have a product. I have an x cubed multiplied by a radical. So one thought of how to integrate this might be to use integration by parts, but we're a little bit luckier than that. In this case, I can actually just do a u substitution. If I let u be equal to the interior of the radical, 1 plus 9x to the fourth, I see that du, the derivative of this, is equal to 36x cubed. Now we're lucky. Most of these surface area problems are going to be like the last problem that we saw, that we'll have to use numerical methods or we could plug into GeoGebra to be able to solve. This is one that we can solve by hand using a u substitution. Notice that I need 36x cubed, but I don't have 36x cubed. So I'm going to change my original integral. I'm not changing the value of it. I'm just going to multiply it by a clever version of 1. I'll multiply the interior by 36 and the exterior by 1 over 36 so that I can rewrite my integral. This is going to be 2 pi divided by 36 times the integral from 0 to 1. And notice I'll be sure to write x equals 0 to 1. My 36x cubed, oops, this dx, I took the derivative with respect to x. These pieces become my du, sorry. du is equal to these pieces. But then this whole big messy front piece is actually just u to the 1/2. And this is something easy to integrate. I can integrate u to the 1/2. That gives me 2 pi over 36, u to the 1/2. I'm going to raise it up and it becomes u to the 3/2. And then I multiply by the reciprocal, 2/3. And this is evaluated as x goes from 0 to 1. Plugging back in for x, coming down here, actually 2/36, that's just pi over 18 times 2/3 of u, but remember that u was just 1 plus 9x to the fourth. Shoomp. All raised to the 3/2. Right? Because I just plugged in what x is, and now I need to evaluate that as x goes from 0 to 1. I'm going to do one more step of simplification, I think. Well, let's just plug it in, and it gets a little messy. Plugging in 1 into here, I end up with 2 pi over, what's 18 times 3? I don't know, so I want to multiply this out first. 2 divided by 18 is 9, and 9 times 3 is 27. Right, so pi over 27 is my outer coefficient. And then I have 1 plus 9 to the 3/2. So I took and evaluated at 1, and now I'm going to subtract out pi over 27 and evaluate it at 0, x equals 0, so I just get 1 to the 3/2. And I can simplify this. This becomes pi over 27 times the quantity 10 to the 3/2 minus 1 to the 3/2 is just 1. And I can type that into my calculator, and I see let's see, 10 to the 3/2 minus 1, and then I want to take that and multiply it by pi over, maybe I'll put parentheses, it won't make a difference, pi divided by 27, and I get that the surface area is about equal to 3.563.